Far beneath the surface of the Atlantic Ocean, where sunlight fades to eternal darkness, lies a region that has captured human imagination for generations. The Bermuda Triangle stretches across vast waters, its invisible boundaries connecting three distant shores: the bustling city of Miami, the remote island of Bermuda, and the tropical coast of Puerto Rico. Within this triangle of ocean, stories have been born that seem to defy explanation. For decades, tales have emerged from these waters like whispers carried on the wind: ships that vanished without a trace, aircraft that disappeared into clear skies, leaving behind only silence, compasses that spun wildly, pointing towards some unknown magnetic force, radio signals that crackled and died. In the collective memory of our world, this stretch of ocean became something more than water and salt. It became a doorway to the impossible. The stories grew with each telling. Sailors spoke of strange lights beneath the waves. Pilots reported instruments failing in perfect weather. Rescue teams searched endless miles of ocean, finding nothing but empty sea. The Bermuda Triangle became a name spoken with equal parts fascination and fear, a place where the laws of nature seemed to bend and break. But what happens when science turns its patient gaze toward mystery? When modern technology peers beneath the surface of legend? When researchers armed with satellites and sonar, with deep-sea submersibles and computer models, begin to examine what lies beneath the myths? Today, as we stand at the edge of understanding, we find ourselves asking new questions. The ocean here is deeper than we once imagined, more complex than our ancestors could have dreamed. The weather patterns are more violent, the currents more unpredictable. The very floor of the sea holds secrets that are only now beginning to emerge. Perhaps the greatest discovery is this: the Bermuda Triangle is not what we thought it was, but it is something far more fascinating. It is a place where the awesome power of nature meets the limits of human understanding, where science and mystery dance together in the deep blue darkness. As we begin this journey into the heart of the triangle, we carry with us the tools of modern discovery and the timeless human need to understand the unknown. The ocean keeps its secrets well, but it is ready to share them with those who listen carefully to the whispers of the deep. On a warm December afternoon in 1945, 5 Navy bombers lifted off from Fort Lauderdale, Florida. Flight 19, as it came to be known, was a routine training mission. The weather was clear, the pilots experienced, the aircraft well-maintained. 2 hours later, Lieutenant Charles Taylor's voice crackled over the radio with words that would echo through history. "We are entering white water. Nothing seems right. We don't know where we are. The water is green, no white." The transmissions grew more desperate, compasses spinning wildly, navigation instruments failing. The pilots, seasoned veterans of World War II, sounded increasingly confused and frightened. Then, silence. 5 aircraft and 14 men vanished without a trace. A rescue plane sent to find them also disappeared, taking 13 more souls into the void. This was not the first mysterious disappearance in these waters, but it would become the most famous. 27 years earlier, the USS Cyclops, a massive Navy cargo ship carrying manganese ore, had vanished somewhere between Barbados and Baltimore. 306 men disappeared with their ship. No distress signal, no wreckage, no explanation. The Cyclops was no ordinary vessel. At 542 feet long, she was one of the largest ships in the Navy's fleet. Her cargo holds were filled with 10,000 tons of manganese ore, bound for the steel mills of Baltimore. Captain George Worley, a veteran mariner with decades of experience, commanded a crew that knew these waters well. Yet on March 4, 1918, the ship simply vanished. The disappearance haunted the Navy for decades. Search planes scoured thousands of square miles of ocean. Ships diverted from their courses to join the hunt. The families of the missing sailors waited for news that would never come. In the official files, the loss was attributed to enemy action, but no German submarine ever claimed the kill. No torpedo had been fired. The great ship had simply sailed into nothingness. These incidents might have remained footnotes in maritime history, curious tragedies in a dangerous profession. But in the 1950s, something began to change. The world was entering a new age of mass media. of sensational headlines and hungry audiences. Writers and journalists discovered that mystery sold newspapers and filled theaters. The transformation began quietly. In 1950, a reporter named E.V.W. Jones wrote an article about the strange disappearances, coining the phrase that would capture imaginations worldwide: the Bermuda Triangle. His piece appeared in the Miami Herald, a local newspaper serving the very waters where these mysteries had unfolded. Jones had spoken to Coast Guard officials, interviewed the families of missing sailors, and pored over official records. His conclusions were measured, his tone cautious. But the story took on a life of its own. Other writers seized upon the theme, each adding their own embellishments. The disappearances became more mysterious, the circumstances more bizarre. What had begun as careful journalism slowly transformed into something else entirely. It was Vincent Gaddis, writing for Argosy magazine in 1964, who truly brought the legend to life. His article, The Deadly Bermuda Triangle, painted a picture of supernatural forces at work in the Atlantic. Gaddis was a skilled writer, a master of atmosphere and suspense. He understood that readers craved mystery in an age of increasing scientific certainty. The stories grew more elaborate with each telling. Writers spoke of alien abductions, of UFOs rising from underwater bases. They described portals to other dimensions, time warps that swallowed ships and planes. The lost city of Atlantis was said to rest beneath the waves, its ancient technology still wreaking havoc on modern vessels. In the pages of these magazines, the Triangle became a realm of impossible phenomena. Pilots reported their instruments spinning wildly, their radios filled with otherworldly static. Ships discovered drifting empty, their crews vanished without explanation, meals still warm on galley tables. The ocean itself seemed alive with malevolent intelligence, but it was Charles Berlitz who transformed local legend into global phenomenon. His 1974 book, The Bermuda Triangle, became an international bestseller, translated into dozens of languages. Berlitz wove together every mysterious disappearance he could find, creating a tapestry of supernatural terror that captivated millions of readers. Berlitz was uniquely positioned to tell this story. The grandson of the founder of the Berlitz language schools, he had grown up in a world of international travel and exotic locations. He spoke multiple languages, had lived in many countries, and possessed a natural gift for storytelling that made even the most outlandish claims seem plausible. The book described electronic fog that could transport ships through time. It told of pilots who found themselves flying through tunnels of light, emerging hours later with no memory of their journey. Ships discovered drifting empty, their crews vanished without explanation. The ocean itself seemed alive with malevolent intelligence. Berlitz presented case after case of mysterious disappearances, each more baffling than the last. He described the disappearance of the Marine Sulphur Queen, a tanker that vanished in 1963. He recounted the story of the Witchcraft, a cabin cruiser that disappeared just 1 mile off Miami Beach. He told of aircraft that vanished in perfect weather, leaving no trace despite massive search efforts. The book struck a chord with readers around the world. In an age of increasing technological sophistication, when humans were walking on the moon and computers were beginning to reshape society, the Bermuda Triangle offered a reminder that mystery still existed. It suggested that despite all our advances, there were still forces beyond our understanding. Yet even as these stories spread around the world, a different picture was emerging in the quiet offices of insurance companies and maritime authorities. Lloyd's of London, the world's most famous maritime insurers, kept meticulous records of every ship lost at sea. Their files told a different story entirely. The statistics were clear and unforgiving. The Bermuda Triangle, despite its fearsome reputation, was no more dangerous than any other heavily traveled shipping lane. The number of vessels lost in these waters was perfectly normal for a region that saw thousands of ships and aircraft pass through each year. The mystery, it seemed, existed only in the imagination. Coast Guard officials, who had spent decades rescuing mariners in distress, spoke with quiet frustration about the myths surrounding their waters. They had investigated every disappearance, followed every lead, searched every mile of ocean. In case after case, they found mundane explanations: human error, equipment failure, sudden storms. Commander Boyd of the Coast Guard's Miami office had personally investigated many of the disappearances cited in Berlitz's book. He found that details had been altered, circumstances exaggerated, and crucial facts omitted. The Witchcraft, for example, had not vanished mysteriously. It had run aground on a well-known sandbar, its crew rescued safely by the Coast Guard. Flight 19, the most famous disappearance of all, had been thoroughly investigated by the Navy. The official report concluded that Lieutenant Taylor had become confused about his position, leading his formation further out to sea instead of toward shore. Radio transmissions revealed his growing disorientation, his refusal to switch to emergency frequencies, his decision to continue east when he should have turned west. But facts, it seemed, were no match for a good story. The Bermuda Triangle had taken on a life of its own, growing stronger with each retelling. It had become something more than a place on the map. It had become a symbol of humanity's eternal fascination with the unknown, a reminder that even in an age of science and technology, mystery still held power over the human heart. The myth had been born from genuine tragedy, nurtured by sensational media and sustained by our deepest fears and wildest hopes. Families had lost loved ones in these waters, sailors had faced real dangers, pilots had encountered genuine navigational challenges. Yet within this tapestry of legend, threads of truth remained. The ocean was indeed dangerous. Weather could change in minutes. Navigation was more challenging than landlubbers could imagine. Perhaps in our hunger for mystery, we had overlooked the most fascinating truth of all, that the natural world was far more complex and unpredictable than any supernatural explanation could ever be. The real Bermuda Triangle was not a realm of alien abductions or time warps. It was something far more remarkable, a meeting place of powerful currents, unpredictable weather, and the endless human drama of those who dare to venture into the deep. If you were to stand on the beaches of Miami on a clear morning and look eastward across the Atlantic, you would be gazing into one corner of an invisible triangle that has captured the world's imagination. The boundaries of this region are not marked by any physical landmarks, no ancient stones or warning buoys. Instead, they exist in the collective consciousness of humanity, connecting three distant points: the bustling metropolis of Miami, the remote coral atoll of Bermuda, and the tropical shores of Puerto Rico. This triangle encompasses roughly 500,000 square miles of ocean, an area larger than the state of Texas. Within these boundaries lies a realm of water that has been traversed by countless ships and aircraft, a crossroads of commerce and adventure that has seen more human activity than perhaps any other stretch of ocean on Earth. Yet to understand the true nature of this region, we must look beyond the myths and legends, beyond the tales of supernatural phenomena, and examine the actual geography that lies beneath the waves. For it is here, in the physical reality of ocean depths and underwater mountains, of powerful currents and shifting sands, that we begin to find the real explanations for the mysteries that have haunted these waters. The western boundary of the triangle begins at Miami, a city that has grown from a small trading post to one of the world's great ports. From here, cargo ships loaded with goods from across the Americas set sail for Europe and beyond. Cruise ships carrying thousands of passengers embark on journeys to tropical paradises. Private yachts and fishing vessels venture into the stream, seeking adventure or livelihood in the deep blue waters. Miami sits at the edge of the continental shelf, where the relatively shallow waters of the Florida coast drop away into the abyss. Just a few miles offshore, the ocean floor plunges from depths of a few hundred feet to several thousand feet, creating underwater cliffs that rival any found on land. This dramatic topography affects everything from weather patterns to ocean currents, creating conditions that can challenge even the most experienced mariners. The northern point of the triangle reaches toward Bermuda, a small island that seems to float alone in the vastness of the Atlantic. 650 miles from the nearest land, Bermuda sits atop an ancient volcanic seamount, surrounded by coral reefs that have claimed countless ships over the centuries. The island is actually composed of more than 150 small islands and islets, connected by bridges and causeways, creating a complex maze of channels and shallow waters. The approach to Bermuda is treacherous even today. The island is surrounded by a nearly continuous barrier of coral reefs that extend for miles in every direction. These reefs, while beautiful to behold, have been the doom of mariners for centuries. The coral rises suddenly from the depths, invisible until it is too late, capable of tearing open the hull of any vessel that ventures too close. The southern boundary extends to Puerto Rico, where the ocean holds perhaps its greatest secret. Here, just north of the island, lies the Puerto Rico Trench, the deepest part of the Atlantic Ocean. This underwater canyon plunges more than 28,000 feet below the surface, deeper than Mount Everest is tall. Within this trench, the ocean floor drops away into darkness so complete that no sunlight has ever penetrated its depths. The Puerto Rico Trench is not merely a curiosity for oceanographers. It represents one of the most geologically active regions in the Atlantic, where the North American and Caribbean tectonic plates meet in a slow-motion collision that has been ongoing for millions of years. This geological activity creates underwater earthquakes, triggers landslides on the ocean floor, and generates the kinds of disturbances that can affect everything from marine life to shipping lanes. Between these 3 points, the ocean floor tells a story of incredible complexity. Underwater mountains rise from the depths, their peaks sometimes coming within a few hundred feet of the surface. Deep valleys cut through the seafloor like ancient riverbeds, channels carved by currents that have flowed for millennia. Vast plains of sediment stretch for hundreds of miles, interrupted by canyons, ridges, and volcanic formations that create a landscape as varied as any found on land. Perhaps the most significant feature of this underwater geography is the Gulf Stream, a massive river of warm water that flows northward along the coast of Florida before turning eastward toward Europe. This current, which can be more than 50 miles wide and 1,500 feet deep, moves at speeds of up to 5 miles per hour, carrying more than 30 times the flow of all the world's rivers combined. The Gulf Stream is not merely a current, but a boundary between two different worlds. To the west lies the relatively warm, shallow water of the continental shelf. To the east stretches the deep, cold water of the Atlantic Basin. This boundary creates a zone of instability where weather systems can form and intensify with startling speed. The warm water of the Gulf Stream carries with it tremendous energy, heat that can fuel the development of powerful storms. During the summer months, this heat combines with atmospheric conditions to create the thunderstorms and tropical cyclones that are a constant threat to navigation in these waters. The contrast between the warm stream and the cooler waters around it creates temperature gradients that can produce sudden fog banks, violent squalls, and unpredictable wind patterns. But the Gulf Stream's influence extends far beyond weather. The current acts as a conveyor belt, rapidly dispersing anything that falls into its waters. Debris from a shipwreck or aircraft crash can be carried hundreds of miles within days, scattered across vast areas of ocean and making recovery efforts nearly impossible. This dispersal effect has contributed to many of the unsolved disappearances in the Triangle, as search teams looking for wreckage often focus their efforts in areas where the debris is no longer located. The depth changes within the Triangle are equally dramatic. Near the coasts of Florida and Puerto Rico, the water is relatively shallow, often less than 200 feet deep, but move just a few miles offshore, and the bottom drops away precipitously. Ships that run into trouble in these areas may sink into waters so deep that they will never be found, their final resting places far beyond the reach of any rescue or salvage operation. These dramatic depth changes also affect the behavior of the ocean itself. Where deep water meets shallow, powerful, upwelling currents can develop, bringing cold water from the depths to the surface. These upwelling zones can create areas of turbulence and unpredictable currents that challenge even modern navigation systems. The continental shelf that extends from the North American coast is carved by numerous underwater canyons, some of which rival the Grand Canyon in size and depth. These canyons, cut by ancient rivers when sea levels were much lower, now serve as conduits for underwater currents and avalanches of sediment. The steep walls of these canyons can create acoustic shadows that interfere with sonar systems, making navigation and communication more difficult. Throughout this region, the ocean floor is littered with the remains of countless ships and aircraft, most of them victims not of supernatural forces, but of the very real dangers posed by this challenging geography. The combination of heavy traffic, difficult navigation, and harsh environmental conditions has made these waters a graveyard for vessels of every description. The triangle sits at the intersection of some of the world's busiest shipping lanes. Every day, hundreds of cargo ships, tankers, and passenger vessels pass through these waters, carrying goods and people between the Americas, Europe, and the Caribbean. The port of Miami alone handles millions of tons of cargo annually, while the nearby Port Everglades serves as a major hub for petroleum products and container ships. This heavy traffic creates its own hazards. In congested shipping lanes, the risk of collision increases dramatically. Large vessels traveling at high speeds have limited ability to maneuver, and in areas where visibility can be reduced by fog or storms, the potential for disaster is ever present. The triangle's position at the crossroads of major shipping routes means that more vessels travel through these waters than almost any other area of comparable size. The aviation routes that crisscross the triangle are equally busy. Miami International Airport serves as a major hub for flights throughout the Americas, while smaller airports in the Bahamas and Caribbean handle thousands of flights annually. The region's position makes it a natural waypoint for aircraft traveling between North and South America, and the constant flow of air traffic creates additional complexity for navigation and air traffic control. Yet despite this heavy traffic, or perhaps because of it, the triangle has developed a reputation for danger that far exceeds the statistical reality. The ocean here is no more treacherous than any other heavily traveled waterway, but the combination of challenging geography, unpredictable weather, and human error creates conditions where accidents are not only possible, but inevitable. The true mystery of the Bermuda Triangle may not be why ships and aircraft disappear, but why so many more do not. Every day, thousands of vessels and aircraft navigate these waters safely, guided by modern technology and the accumulated wisdom of centuries of maritime experience. The Triangle's reputation has been built on the relatively few incidents that have occurred, not on the countless safe passages that happen without notice or fanfare. As we peer deeper into the Triangle's geography, we begin to see not a realm of supernatural danger, but a complex marine environment where natural forces create very real hazards. The ocean floor rises and falls in dramatic formations. Currents flow with tremendous power, and the meeting of different water masses creates conditions that can challenge even the most advanced navigation systems. This is not magic but physics, not mystery but the predictable result of natural processes that have been shaping this region for millions of years. Understanding the true geography of the Triangle does not diminish its fascination, but rather enhances it. The real ocean is far more complex and dynamic than any supernatural explanation could ever be. In the interplay of currents and depths, of weather and geology, we find a story that is both more believable and more wonderful than any tale of alien abductions or time warps. The Triangle's power to capture our imagination lies not in its supernatural reputation, but in its role as a window into the awesome forces that shape our planet's oceans. Above the waters of the Bermuda Triangle, the sky holds its own secrets. Here, where warm tropical air meets the cooler currents of the Atlantic, the atmosphere becomes a theater of dramatic performances that can unfold with breathtaking speed and devastating power. To understand the mysteries that have plagued these waters, we must turn our gaze upward to the realm where clouds are born and storms take shape. The Triangle sits at a unique crossroads of atmospheric conditions, a meeting place where different air masses collide and dance in patterns that meteorologists are only beginning to fully understand. The warm, humid air that rises from the tropical waters of the Caribbean encounters the cooler, drier air that flows southward from the North American continent. When these air masses meet, they create a zone of instability that can spawn weather phenomena ranging from gentle rain showers to catastrophic hurricanes. Perhaps no weather phenomenon is more feared by pilots than the microburst, a localized downdraft of air that can develop with little warning and strike with the force of a sledgehammer. These invisible columns of descending air can reach speeds of over 100 miles per hour, creating a cone of destruction that extends from the clouds to the surface of the ocean. For an aircraft caught in a microburst, the experience is like being grabbed by a giant hand and hurled toward the water. Microbursts develop when rain or hail begins to fall from a thundercloud but evaporates before reaching the surface. This evaporation cools the air, making it denser and heavier than the surrounding atmosphere. The cooled air plunges downward like a stone dropped into water, accelerating as it falls until it strikes the surface with tremendous force. Upon impact, the downdraft spreads outward in all directions, creating a pattern of winds that can shift from headwind to tailwind in a matter of seconds. For pilots flying at low altitudes, micro-bursts present a nightmare scenario. As an aircraft enters the downdraft, it experiences a sudden increase in headwind that causes it to climb. Pilots feeling their aircraft rising unexpectedly often reduce power to maintain their desired altitude. But as the aircraft passes through the center of the microburst and encounters the downdraft, it begins to lose altitude rapidly. When the pilot attempts to add power to arrest the descent, the aircraft emerges into a severe tailwind that further reduces lift and makes recovery nearly impossible. The triangle's position makes it particularly susceptible to microburst activity. The contrast between the warm water of the Gulf Stream and the cooler air above creates ideal conditions for the development of these sudden downdrafts. During the summer months, when atmospheric instability is at its peak, microbursts can develop almost anywhere within the triangle, often with no advance warning from conventional weather radar. Equally dangerous are the rogue waves that can appear without warning in even moderately rough seas. These massive walls of water, sometimes reaching heights of 60 feet or more, can overwhelm vessels that are perfectly capable of handling normal ocean swells. Unlike the regular wave patterns that mariners learn to read and navigate, rogue waves appear suddenly, often in groups of 3 or more, and can strike from directions that seem to defy the prevailing sea conditions. The formation of rogue waves is a complex process that scientists are still working to understand fully. They appear to result from the constructive interference of multiple wave systems, where waves traveling in different directions meet and combine their energy into a single towering mass of water. The triangle's position at the confluence of different current systems creates ideal conditions for this type of wave interaction. The Gulf Stream itself contributes to rogue wave formation by creating areas where fast-moving current encounters opposing winds. When strong winds blow against the direction of the current, they can create steep, unstable waves that are prone to combining into larger formations. The result is a sea state that can change from manageable to life-threatening in a matter of minutes. Modern satellite imagery has revealed that the triangle experiences some of the most complex and rapidly changing weather patterns anywhere on Earth. High-resolution images show spiral formations of clouds that appear and dissipate within hours, atmospheric disturbances that seem to materialize from nothing and vanish just as quickly. These images reveal a dynamic atmosphere in constant motion, where stability is the exception rather than the rule. The phenomenon known as atmospheric gravity waves adds another layer of complexity to the triangle's weather patterns. These are not the gravitational waves predicted by Einstein's theory of relativity, but rather oscillations in the atmosphere caused by the interaction of air masses with different densities. When stable air is forced to rise over a barrier such as a weather front or temperature gradient, it can create waves that propagate through the atmosphere like ripples on a pond. Atmospheric gravity waves can travel for hundreds of miles, carrying energy and moisture across vast distances. When these waves encounter the right conditions, they can trigger the rapid development of thunderstorms or other severe weather phenomena. The triangle's position makes it a natural focal point for these atmospheric disturbances, as waves generated by weather systems throughout the Atlantic basin converge on this region. The seasonal hurricane activity that affects the triangle is perhaps the most well-documented of its weather hazards. From June through November, the warm waters of the Atlantic serve as fuel for tropical cyclones that can grow from minor disturbances to Category 5 monsters in a matter of days. The triangle lies directly in the path of hurricanes that form off the coast of Africa and strengthen as they cross the Atlantic. But hurricanes are not the only tropical weather phenomena that affect these waters. Tropical waves, areas of low pressure that move westward across the Atlantic, can create sudden squalls and severe thunderstorms even when they do not develop into full hurricanes. These disturbances can generate winds of 50 to 70 miles per hour and spawn waterspouts that pose a significant threat to both aircraft and surface vessels. Waterspouts are essentially tornadoes that form over water, columns of rotating air that extend from the base of cumulus clouds to the ocean surface. While generally less powerful than their land-based cousins, waterspouts can still pack winds of over 100 miles per hour and create a vortex capable of damaging or destroying small aircraft and boats. The triangle's warm waters and unstable atmospheric conditions make it one of the most active waterspout regions in the world. The phenomenon of explosive cyclogenesis, sometimes called a weather bomb, represents one of the most dramatic examples of rapid weather development that can occur in the triangle. This process involves the rapid intensification of a low-pressure system, with the central pressure dropping by at least 24 millibars in 24 hours. The result is a storm that can reach hurricane force intensity within a single day, often catching mariners and aviators completely unprepared. Temperature inversions add yet another dimension to the triangle's atmospheric complexity. These occur when a layer of warm air sits atop cooler air near the surface, creating a stable atmospheric condition that can trap moisture, pollutants, and even radio signals. Inversions can create optical illusions that make distant objects appear closer or farther than they actually are, leading to navigation errors and pilot disorientation. The interaction between the ocean and atmosphere in the triangle creates feedback loops that can amplify weather disturbances. Warm water evaporates rapidly, adding moisture to the air and providing energy for storm development. As storms form and intensify, they can create areas of upwelling that bring cooler water to the surface, which can then affect subsequent weather patterns. This constant exchange of energy between sea and sky creates a dynamic system where small changes can have large and unpredictable effects. Modern meteorology has made great strides in understanding and predicting these atmospheric phenomena, but the triangle's weather still poses significant challenges. The rapid development of severe weather can outpace even the most sophisticated forecasting models, and the complex interactions between different atmospheric systems can create conditions that are difficult to predict with certainty. Satellite technology has revolutionized our ability to observe and track weather patterns in the triangle. High-resolution images can capture the formation of individual thunderstorms, the development of tropical systems, and the movement of atmospheric disturbances across the region. Doppler radar systems can detect the presence of microbursts, waterspouts, and other severe weather phenomena, providing advance warning to pilots and mariners. Yet despite these technological advances, the atmosphere above the triangle remains a realm of surprising complexity and occasional violence. The weather here is not supernatural, but it is undeniably powerful. The combination of warm tropical waters, complex current systems, and variable atmospheric conditions creates an environment where severe weather can develop rapidly and strike with little warning. The key to understanding the triangle's reputation may lie not in supernatural explanations, but in the very real and documented power of its atmospheric phenomena. Microbursts, rogue waves, explosive cyclogenesis, and rapid storm development can all create conditions that are dangerous enough to account for aircraft and vessel losses without invoking any paranormal causes. For those who venture into these waters, whether by sea or air, the atmosphere above the triangle demands respect and careful preparation. Modern weather forecasting and detection equipment have made navigation safer, but they cannot eliminate the fundamental reality that this region experiences some of the most dynamic and potentially dangerous weather patterns on Earth. The sky above the triangle tells a story of constant change and occasional violence, of atmospheric forces that can transform a clear day into a life-threatening situation in a matter of minutes. Understanding these forces does not diminish the mystery of the triangle, but rather reveals it to be a place where the raw power of nature is on constant display, a reminder that even in our age of advanced technology, the atmosphere still holds the power to surprise and humble those who dare to challenge it. In the end, the greatest mystery of the triangle's weather may not be its occasional violence, but its incredible complexity. Here, in this relatively small patch of ocean, we can observe the full spectrum of atmospheric phenomena, from gentle trade winds to devastating hurricanes. The triangle serves as a natural laboratory where meteorologists can study the intricate dance between ocean and atmosphere, a dance that has been going on for millions of years and will continue long after the last ship has crossed these waters. Deep beneath the waves of the Bermuda Triangle, in the cold darkness where sunlight has never penetrated, lies a substance that exists at the very edge of stability. Methane hydrate, sometimes called fire ice, represents one of the most intriguing and potentially dangerous phenomena hidden within the ocean floor. These crystalline structures formed under the extreme pressure and cold of the deep sea hold within them the power to transform solid seabed into a churning mass of gas and water in a matter of moments. To understand methane hydrates, we must journey to the bottom of the ocean, where temperatures hover just above freezing, and the weight of miles of water above creates pressures that would crush any surface dweller in an instant. Here, in these alien conditions, water molecules arrange themselves into cage-like structures that trap molecules of methane gas, creating a solid that looks remarkably like ice, but burns with a bright flame when brought to the surface. The formation of these hydrates is a process that has been occurring for millions of years. Organic matter, the remains of ancient sea life, settles onto the ocean floor and becomes buried under layers of sediment. As bacteria break down this organic material in the oxygen-free environment of the deep seabed, they produce methane gas. Under the right conditions of temperature and pressure, this methane combines with water to form the crystalline structures we know as methane hydrates. These deposits are not merely scientific curiosities. Estimates suggest that methane hydrates may contain more energy than all other fossil fuel reserves combined, representing a vast and largely untapped resource that lies hidden beneath the world's oceans. The deposits are particularly abundant along continental margins, where the ocean floor drops away from shallow coastal waters into the abyssal depths. Within the boundaries of the Bermuda Triangle, the conditions for methane hydrate formation exist in several locations. The continental slope off the coast of Florida, the deep waters surrounding Bermuda, and the Puerto Rico Trench all contain areas where these mysterious substances may be found. The combination of cold temperatures, high pressure, and organic-rich sediments creates an environment where methane hydrates can form and accumulate over geological timescales, but these deposits are inherently unstable. The crystalline structure that holds the methane in solid form exists only within a narrow range of temperature and pressure conditions. If the temperature rises by just a few degrees, or if the pressure decreases suddenly, the hydrates can decompose rapidly, releasing vast quantities of methane gas into the surrounding water. This process of decomposition can have dramatic effects on the ocean itself. When methane hydrates break down, they release gas that rises toward the surface in the form of bubbles. These bubbles displace water, reducing the density of the surrounding sea. A ship floating in water suddenly filled with methane bubbles can experience a catastrophic loss of buoyancy, causing it to sink rapidly with little warning. Laboratory experiments have demonstrated the dramatic effect that methane release can have on a vessel's ability to stay afloat. Scale models of ships placed in water where methane is being released have been observed to lose buoyancy almost instantly, sinking like stones despite being perfectly seaworthy under normal conditions. The effect is so pronounced that even large vessels could potentially be affected if they encountered a sufficiently large release of methane. The mechanism behind this phenomenon is relatively straightforward. Water is a dense fluid that provides buoyancy through the principle of displacement discovered by Archimedes more than 2,000 years ago. When methane bubbles fill the water around a ship, they reduce the overall density of the fluid, making it less capable of supporting the vessel's weight. The effect is similar to what happens when a person tries to float in water filled with air bubbles from a jacuzzi jet. Several factors could trigger the release of methane from hydrate deposits. Underwater earthquakes, which are common along the tectonically active margins of the Atlantic, could destabilize hydrate formations and cause massive releases of gas. Changes in ocean temperature, perhaps caused by shifting currents or climate variations, could also trigger decomposition. Even human activities such as deep-sea drilling or the passage of large ships could potentially disturb these delicate formations. The Puerto Rico Trench, which forms part of the triangle's southern boundary, is particularly susceptible to seismic activity. This region sits at the boundary between tectonic plates, where the slow but inexorable movement of the Earth's crust creates stress that is periodically released in the form of earthquakes. These underwater tremors could easily trigger the release of methane from hydrate deposits along the steep slopes of the trench. Some researchers have suggested that methane releases could explain some of the mysterious disappearances that have been attributed to the Bermuda Triangle. The sudden loss of buoyancy caused by a large methane release could cause a ship to sink so rapidly that there would be no time to send a distress signal. the vessel would simply vanish beneath the waves, leaving no trace except perhaps a brief disturbance on the ocean surface. However, the scientific community remains divided on whether methane hydrates could realistically account for ship disappearances in the triangle. While the theoretical possibility exists, several factors make such events unlikely in this particular region. The water temperatures in much of the triangle are too warm to support stable hydrate formations near the surface. Most methane hydrate deposits in the area would be found at depths of several thousand feet, far below the level where they could directly affect surface vessels. Moreover, for a methane release to be large enough to sink a substantial ship, the hydrate deposits would need to be both extensive and unstable. While hydrates do exist in the Atlantic, they are generally found in deeper, colder waters than those that characterize much of the triangle. The warm tropical and subtropical waters that dominate this region are not conducive to the formation of large, shallow hydrate deposits. Recent advances in deep-sea exploration have allowed scientists to study methane hydrates more directly than ever before. Remotely operated vehicles equipped with sophisticated sensors can descend to the ocean floor and examine hydrate formations in their natural environment. These studies have revealed that while hydrate deposits are indeed widespread, they are generally stable under current ocean conditions. The process of methane seepage from the ocean floor is not uncommon and occurs in many parts of the world's oceans. In most cases, this seepage is gradual and continuous, with small amounts of gas being released over extended periods. The methane typically dissolves in the seawater or is consumed by bacteria before reaching the surface, making dramatic releases relatively rare events. Computer simulations have been used to model the potential effects of large methane releases on ship stability. These studies suggest that while a sufficiently large release could indeed affect a vessel's buoyancy, the size of the release required would be enormous. The methane would need to be released over a large area and reach a significant concentration in the water column to have a noticeable effect on a ship's ability to float. Furthermore, such a large release would likely leave detectable traces. Methane is a greenhouse gas that can be measured in the atmosphere, and a major release from the ocean floor would likely result in elevated methane concentrations in the air above the release site. Satellite instruments designed to monitor atmospheric composition would likely detect such an event, yet no such detections have been associated with unexplained ship disappearances in the triangle. The study of methane hydrates has also revealed their potential role in climate change. These deposits represent a vast reservoir of carbon that could be released into the atmosphere if ocean temperatures continue to rise. The warming of deep ocean waters could destabilize hydrate formations worldwide, releasing methane that would contribute to further warming in a potentially dangerous feedback loop. Despite the dramatic potential of methane hydrates, most scientists believe that they cannot account for the reputation of the Bermuda Triangle. The conditions required for massive methane releases are simply not present in most of the triangle's waters. The region's reputation appears to be based more on myth and selective reporting than on any real increase in maritime disasters. This does not mean that methane hydrates are irrelevant to understanding the ocean environment. These remarkable substances represent one of the frontier areas of marine science, offering insights into the complex chemical and physical processes that occur in the deep sea. As technology continues to improve, scientists are gaining new appreciation for the role that hydrates play in ocean chemistry and marine ecosystems. The search for alternative energy sources has renewed interest in methane hydrates as a potential fuel source. Several countries, including Japan and South Korea, have conducted experimental programs to extract methane from hydrate deposits. These efforts have shown that it is technically possible to recover methane from hydrates, though the process remains challenging and expensive. For the Bermuda Triangle, methane hydrates remain an intriguing but unlikely explanation for its mysterious reputation. While these substances do exist in the deep waters surrounding the region, they are not present in sufficient quantities or in the right locations to account for surface ship disappearances. The real significance of hydrates may lie not in their potential to sink ships, but in their role as indicators of the complex and still poorly understood processes that occur in the deep ocean. The ocean floor beneath the triangle holds many secrets, from ancient coral reefs to volcanic formations, from sediment layers that record millions of years of history, to chemical processes that continue to shape the marine environment. Methane hydrates are just one part of this complex system, a reminder that the deep sea remains one of the least explored regions on our planet. As we continue to probe the mysteries of the deep ocean, methane hydrates serve as a symbol of how much we still have to learn about our planet's marine environment. These strange substances existing at the boundary between solid and gas, between stability and chaos, remind us that the ocean holds wonders that are far more remarkable than any supernatural explanation for the triangle's reputation. The true mystery of methane hydrates may not be their potential to explain disappearances in the triangle, but their role in the larger story of how our planet's oceans function. In these crystalline structures, formed in the crushing depths and bitter cold of the abyss, we find a reminder that Earth's systems are far more complex and interconnected than we might imagine, operating on scales of time and space that dwarf human experience, yet influence every aspect of our world. In the age before satellites and global positioning systems, mariners and aviators navigated by the stars and by the invisible lines of force that emanate from the Earth's magnetic field. The compass, that simple instrument of magnetized metal floating in fluid, served as humanity's guide across the trackless expanses of ocean and sky. Yet within the boundaries of the Bermuda Triangle, this fundamental tool of navigation has long been the subject of mysterious tales and confusing reports. Stories have persisted for decades of compass needles spinning wildly, of instruments pointing in impossible directions, of navigational equipment failing without explanation. Pilots have reported flying in clear skies with perfect visibility, only to find their compasses disagreeing with their charts, leading them far from their intended course. Ships have allegedly wandered off course despite experienced crews and properly maintained equipment, as if drawn by some invisible force toward an unknown destination. To understand these phenomena, we must first understand the nature of the Earth's magnetic field itself. Our planet acts as a giant magnet, with magnetic poles that are distinct from the geographic poles around which the Earth rotates. The magnetic field is generated deep within the Earth's core, where the movement of molten iron creates electrical currents that produce magnetism on a planetary scale. This magnetic field is not uniform across the Earth's surface. It varies in strength and direction depending on location, geological features, and temporal changes within the Earth's core. The difference between magnetic north, where a compass points, and true north, the geographic pole, is called magnetic declination or variation. This difference changes depending on where you are on Earth and has been slowly shifting over time as the magnetic field itself evolves. In the early days of navigation, understanding and compensating for magnetic variation was crucial for accurate position finding. Charts were marked with isogonic lines showing the magnetic variation for different locations, and navigators had to carefully calculate the difference between magnetic and true bearings when plotting their course. Even small errors in this calculation could lead vessels far from their intended destination over long distances. The Bermuda Triangle sits in a region where magnetic variation has historically been significant and changeable. During certain periods in the past, this area was one of the few places on Earth where magnetic north and true north aligned closely, creating what navigators called the agonic line. Along this line, compass readings would closely match true geographic directions without the need for correction. However, the Earth's magnetic field is not static. The magnetic poles wander slowly over time, and the agonic line shifts accordingly. What was once a region of minimal magnetic variation has gradually changed, and the alignment between magnetic and true north that may have existed in the triangle decades ago has long since disappeared. Modern magnetic surveys have revealed that the triangle does experience variations in magnetic field strength and direction, but these variations are not unique to this region. Similar magnetic anomalies can be found in many parts of the world, often associated with underlying geological features such as iron ore deposits, volcanic formations, or areas where different types of rock meet beneath the ocean floor. The continental shelf that underlies much of the triangle contains geological formations that can affect local magnetic readings. Ancient lava flows, now buried beneath sediment, can create areas of stronger or weaker magnetic field strength. Iron-rich minerals in the seafloor can cause compass deviations, particularly in areas where these deposits are close to the surface. One of the most significant factors affecting navigation in the triangle is not the magnetic field itself, but the complex interaction between magnetic variation, ocean currents, and wind patterns. The Gulf Stream, that massive river of warm water flowing northward along the coast, can push vessels eastward even when they believe they are maintaining a steady course. Without careful attention to current set and drift, navigators can find themselves miles from their intended position. During the era when the disappearances that built the triangle's reputation occurred, navigation was far more challenging than it is today. Pilots and mariners relied heavily on dead reckoning, estimating their position based on course, speed, and time traveled from a known starting point. This method, while effective under ideal conditions, was vulnerable to errors that could accumulate over time and distance. Weather conditions in the triangle can exacerbate navigational challenges. Cloud cover can make celestial navigation impossible, forcing pilots and mariners to rely entirely on their instruments. Poor visibility due to fog, rain, or haze can make it difficult to spot landmarks or other vessels that might help confirm position. In such conditions, even small compass errors can lead to significant navigation problems. The famous case of Flight 19 illustrates how navigational confusion can escalate into disaster. Lieutenant Charles Taylor, the flight leader, became convinced that his compass was malfunctioning when he found himself over unfamiliar terrain. His radio transmissions reveal a growing sense of disorientation as he struggled to reconcile what he was seeing with what his instruments were telling him. What Taylor may not have fully appreciated was that compasses can be affected by numerous factors beyond magnetic anomalies. Electrical systems in aircraft can create magnetic interference that affects compass readings. Metal objects within the aircraft, changes in heading, acceleration, and turbulence can all cause temporary compass deviations. Even the aircraft's fuel load, as it decreases during flight, can affect the magnetic environment around the compass. Modern aircraft and ships use gyroscopic compasses that are not affected by magnetic fields, but these instruments have their own limitations. Gyro compasses must be properly aligned and maintained, and they can drift over time if not regularly corrected. During the era when many of the triangle's mysterious disappearances occurred, such sophisticated equipment was not widely available, and magnetic compasses remained the primary navigational tool. The introduction of radio navigation aids revolutionized navigation in the triangle and elsewhere. Radio beacons on land could provide bearing information to aircraft and ships equipped with radio direction-finding equipment. Later, systems like LORAN, which used the time difference between radio signals from multiple transmitters to determine position, provided much more accurate navigation than had previously been possible. However, radio navigation systems have their own vulnerabilities. Atmospheric conditions can affect radio wave propagation, causing signals to bend or bounce in unexpected ways. During certain weather conditions, radio signals can travel much farther than normal, causing navigators to receive signals from distant transmitters and leading to position errors. The triangle's position in an area of frequent atmospheric disturbances makes such radio anomalies more likely. Satellite navigation systems like GPS have largely eliminated the navigation problems that may have contributed to the triangle's reputation. These systems provide position accuracy to within a few meters anywhere on Earth, regardless of weather conditions or magnetic anomalies. Modern aircraft and ships equipped with GPS are far less likely to become lost than their predecessors that relied on magnetic compasses and dead reckoning. Yet even GPS is not infallible. Solar storms can disrupt satellite signals, and atmospheric conditions can affect signal accuracy. Military operations sometimes involve GPS jamming or spoofing, though such activities are unlikely to affect civilian navigation in the triangle. For this reason, experienced navigators still maintain backup navigation methods and continue to monitor traditional navigation aids. Scientific studies of the Earth's magnetic field in the Triangle region have found no evidence of unusual magnetic phenomena that could not be explained by normal geological processes. Magnetic surveys conducted by government agencies and research institutions have mapped the magnetic variations in the area in great detail, revealing patterns that are consistent with the underlying geology and the normal behavior of the Earth's magnetic field. The World Magnetic Model, updated every 5 years by geophysical agencies, provides accurate predictions of magnetic field behavior across the globe, including the Triangle region. This model shows that while magnetic variation does exist in the area, it is well within normal parameters and poses no unusual challenges to modern navigation systems. Some researchers have suggested that the triangle's reputation for compass anomalies may stem from the psychological effects of expectation and confirmation bias. Pilots and mariners who are aware of the triangle's reputation may be more likely to notice and report compass irregularities that they might otherwise ignore. Normal compass behavior that would be unremarkable in other locations may seem significant when it occurs within the triangle's boundaries. The human factor in navigation cannot be underestimated. Fatigue, stress, and disorientation can affect a navigator's ability to read instruments accurately or make proper calculations. In emergency situations, when time is critical and stress levels are high, even experienced navigators can make errors that they would never make under normal circumstances. Training and experience play crucial roles in navigation accuracy. Pilots and mariners who are familiar with local conditions, magnetic variations, and potential hazards are far less likely to encounter navigation problems than those who are unfamiliar with the area. The triangle's position as a crossroads for international travel means that it sees many transient operators who may not be familiar with local conditions. Modern navigation training emphasizes the importance of using multiple navigation methods and cross-checking position information from different sources. This redundancy helps prevent the kind of navigation errors that may have contributed to some of the disappearances that built the triangle's reputation. Today's navigators are taught to question any single source of information and to verify their position using multiple independent methods. The magnetic compass remains an important backup navigation tool even in the age of GPS. Properly understood and correctly used, it is a reliable instrument that has guided travelers safely across the Earth's surface for thousands of years. The key is understanding its limitations and knowing how to compensate for the various factors that can affect its accuracy. Electronic navigation systems have also introduced new types of potential errors. Software bugs, database errors, and equipment failures can cause modern navigation systems to provide incorrect information. While such failures are rare, they highlight the importance of maintaining traditional navigation skills and backup systems. The triangle's magnetic environment, while not supernatural, does present real challenges that require knowledge and skill to navigate safely. Understanding magnetic variation, recognizing the signs of compass problems, and knowing how to use alternative navigation methods are all important skills for anyone operating in these waters. As we have seen throughout this exploration of navigation in the Triangle, the challenges are real but not mysterious. They are the same challenges that face navigators anywhere in the world: understanding the environment, properly maintaining equipment, and developing the skills necessary to use navigation tools effectively. The Triangle's reputation may have been built on navigation errors and equipment failures, but these are problems that can be solved through proper training, adequate equipment, and careful attention to the principles of safe navigation. The invisible lines of magnetic force that crisscross the Triangle continue to guide travelers as they have for centuries. Understanding these forces and learning to work with them rather than against them remains one of the fundamental skills of seamanship and airmanship. In this understanding, we find not mystery, but mastery, not supernatural danger, but the satisfaction of human skill triumphing over natural challenges. In the realm of human imagination, where logic bends and possibilities stretch beyond the boundaries of known science, the Bermuda Triangle has become a canvas upon which we paint our deepest fears and wildest dreams. Here, in the stories told in hushed voices and printed in dog-eared paperbacks, the Triangle transforms from a patch of ocean into something far more extraordinary. A doorway to other worlds, a hunting ground for beings from distant stars, a place where time itself becomes unstable. These theories, born from the marriage of mystery and imagination, speak to something fundamental in the human spirit. They represent our desire to believe that the universe holds wonders beyond our current understanding, that reality is far stranger and more magical than the mundane world of scientific measurement and rational explanation. In exploring these ideas, we explore not just the Triangle itself, but the very nature of human curiosity and our eternal quest to find meaning in the unknown. The theory of extraterrestrial involvement in triangle disappearances emerged in the 1960s and 70s, during an era when UFO sightings were capturing public attention around the world. Writers and researchers began to suggest that the disappearances might be the work of alien visitors, either accidentally interfering with human technology or deliberately collecting specimens for unknown purposes. According to these theories, advanced extraterrestrial civilizations had established underwater bases beneath the triangle's waters. These hidden installations, perhaps located in the deepest trenches or concealed by sophisticated cloaking technology, served as staging areas for alien operations on Earth. Ships and aircraft that ventured too close to these bases might be captured, their crews taken for study, or their technology examined by beings whose science transcended human understanding. The underwater base theory drew support from scattered reports of unusual lights beneath the ocean surface, mysterious objects emerging from or diving into the water, and electromagnetic anomalies that seemed to defy conventional explanation. Witnesses described seeing disc-shaped craft rising from the waves, trailing water and steam as they accelerated into the sky at impossible speeds. Others reported encounters with structured objects moving beneath the surface, visible only as moving lights or unusual disturbances in the water. Some proponents of the alien theory suggested that the extraterrestrials were not hostile but simply indifferent to human welfare. In their view, the disappearances were side effects of alien activities rather than deliberate actions. Perhaps human technology was incompatible with alien energy fields, causing aircraft engines to fail or ship electronics to malfunction at critical moments. Perhaps the aliens were conducting experiments that inadvertently affected human vessels passing through the area. More elaborate versions of the alien theory proposed that the triangle served as a collection point for an ongoing study of human civilization. According to this scenario, extraterrestrial scientists were gathering samples of human technology, culture, and biology to better understand Earth's dominant species. The missing ships and aircraft were not destroyed but transported to alien facilities, possibly on other worlds, where they could be studied in detail. The portal theory represents another category of supernatural explanation, suggesting that the triangle contains rifts in the fabric of space and time that allow passage between different dimensions or realities. These theoretical gateways might open randomly or in response to specific conditions, swallowing any vessel unfortunate enough to encounter them at the wrong moment. Proponents of portal theories often pointed to reports of time distortion within the triangle. Pilots claimed to have experienced flights that took much less time than should have been possible, as if they had somehow bypassed normal space to reach their destinations. Others reported the opposite effect, finding that journeys through the triangle took far longer than expected, with no explanation for the missing time. The most dramatic portal accounts involved claims of time travel or dimensional displacement. Stories circulated of pilots who emerged from cloud formations to find themselves flying over landscapes that seemed subtly different from what they remembered, or of ships that arrived at their destinations with calendar dates that did not match the time they believed had passed during their voyage. Some versions of the portal theory suggested that the triangle contained access points to parallel dimensions where the laws of physics operated differently. In these alternate realities, the same geographic locations might exist, but with different histories, different civilizations, or different natural laws. Vessels passing through these portals might find themselves in worlds that were recognizably Earth-like, but fundamentally changed. The time slip theory proposed that the triangle contained areas where the normal flow of time became unstable. In these zones, past, present, and future might overlap or become confused, causing vessels to slip between different temporal periods. Ships from the present might find themselves in the past or future, while vessels from other eras might occasionally appear in modern times before vanishing again into their proper temporal locations. These temporal anomalies were sometimes attributed to natural phenomena that science had not yet discovered, exotic forms of energy or matter that could affect the passage of time in localized areas. Proponents suggested that the unique geological and oceanographic features of the triangle might create conditions conducive to these temporal distortions, making it a natural laboratory for time-related phenomena. The Atlantis connection represents one of the most enduring supernatural explanations for triangle mysteries. According to this theory, the legendary lost civilization of Atlantis lies beneath the triangle's waters, and its advanced technology continues to function despite the passage of millennia. This ancient technology, far beyond anything achieved by modern science, supposedly interferes with contemporary vessels passing overhead. Supporters of the Atlantis theory pointed to the presence of unusual formations on the ocean floor, which they interpreted as the ruins of ancient cities or technological installations. They suggested that Atlantean energy sources, perhaps based on crystal technology or other exotic principles, created fields of force that could disable modern engines, disrupt electronics, or even disintegrate matter itself. Some versions of this theory proposed that the Atlanteans had not died out, but had retreated to underwater cities where they continued to develop their advanced civilization. These hidden Atlanteans might view surface dwellers as primitives whose vessels posed a threat to their concealed society, leading them to eliminate any ships or aircraft that came too close to their domain. The psychological dimension of these supernatural theories cannot be ignored. Reports of strange phenomena in the triangle often involve elements that suggest altered states of consciousness or perceptual distortion. Pilots flying at high altitudes can experience hypoxia, a condition caused by insufficient oxygen that can lead to confusion, hallucinations, and poor judgment. The vast emptiness of ocean and sky can create sensory deprivation that affects perception and memory. Disorientation at sea is a well-documented phenomenon that can affect even experienced mariners. The monotonous environment of open ocean, combined with fatigue, stress, and isolation, can lead to temporal confusion, visual hallucinations, and altered perception of reality. Under such conditions, normal phenomena might be interpreted as supernatural, and memory of events might become distorted or unreliable. The power of suggestion also plays a role in supernatural reports. Pilots and mariners who are aware of the triangle's reputation may be primed to interpret unusual but explainable events as paranormal phenomena. What might otherwise be dismissed as equipment malfunction, weather effects, or simple misperception becomes significant when it occurs within the triangle's supposed boundaries. Cultural factors influence how these theories develop and spread. The triangle's supernatural reputation emerged during a period of intense interest in UFOs, ancient astronauts, and paranormal phenomena. Television shows, movies, and books exploring these themes found eager audiences, and the triangle became a focal point for speculation about mysterious forces and hidden realities. The appeal of supernatural explanations often lies in their ability to provide meaning and significance to otherwise random events. A ship lost in a storm is a tragedy, but a ship taken by aliens or transported to another dimension becomes part of a larger cosmic drama. These theories transform victims of accidents or natural disasters into participants in grand adventures or cosmic experiments. Despite decades of investigation by believers and skeptics alike, no conclusive evidence has been found to support any of the supernatural theories surrounding the triangle. No alien artifacts have been recovered from the ocean floor. No temporal anomalies have been detected by sensitive instruments. No portals to other dimensions have been photographed or measured. The triangle's reputation remains based on anecdotal reports, selective interpretation of evidence, and the enduring human fascination with mystery. This lack of physical evidence does not necessarily diminish the cultural significance of these theories. They reflect deep-seated human needs and desires, the hope that we are not alone in the universe, the belief that reality contains hidden wonders, the desire to transcend the limitations of ordinary existence. In this sense, the supernatural theories of the triangle serve important psychological and cultural functions regardless of their factual accuracy. The scientific method requires theories to be testable and falsifiable, criteria that most supernatural explanations fail to meet. Alien bases that cannot be detected, portals that open randomly, and time slips that leave no measurable trace exist beyond the reach of empirical investigation. This does not make them impossible, but it does place them outside the realm of science as currently understood. Modern technology has made many of the phenomena described in supernatural theories increasingly difficult to maintain. Satellite surveillance monitors the Earth's surface continuously, making hidden alien bases or mysterious islands virtually impossible to conceal. GPS systems track the movement of aircraft and ships with unprecedented precision, making claims of time distortion or dimensional displacement easier to verify or refute. Yet the theories persist, adapting to new evidence and evolving with changing cultural interests. When satellite imagery fails to reveal alien bases, proponents suggest more sophisticated cloaking technology. When GPS fails to confirm time anomalies, they propose that the technology itself is affected by the mysterious forces at work in the triangle. The enduring appeal of these supernatural theories may lie not in their literal truth but in their symbolic power. They represent humanity's refusal to accept that all mysteries can be reduced to mundane explanations, our insistence that wonder and magic have a place in the universe. In an age of increasing scientific knowledge and technological capability, the triangle serves as a reminder that there are still questions without answers, still rooms in the mansion of reality that remain unexplored. Whether we view these theories as delightful fantasies or misguided beliefs, they form an integral part of the triangle's cultural legacy. They have inspired countless works of fiction, launched numerous expeditions and investigations, and provided endless material for speculation and debate. In this sense, they have been far more successful than many scientific theories in capturing the public imagination and influencing popular culture. The true significance of the supernatural theories may be what they reveal about human nature itself. In our willingness to believe in aliens and portals, in our eagerness to find mystery in the mundane, we see reflected our deepest hopes and fears about our place in the universe. The triangle becomes a mirror in which we glimpse not just the ocean's mysteries, but the mysteries of our own hearts and minds. In the depths of the Bermuda Triangle, where eternal darkness reigns and pressure would crush any surface dweller, a revolution has been quietly unfolding. Advanced technology, guided by human curiosity and powered by sophisticated engineering, has begun to pierce the veil that has long shrouded the ocean floor. Autonomous submarines glide through the abyss like mechanical fish, their lights cutting through water that has known only blackness for millions of years. Sonar systems map the seafloor with precision that would have seemed impossible just decades ago, revealing secrets that have waited centuries to be discovered. This technological awakening has transformed our understanding of what lies beneath the triangle's waters. Where once there were only questions and speculation, now there are answers written in sonar images and captured in high-definition video. The ocean floor, previously hidden and mysterious, has become an open book for those with the tools to read it. And what that book reveals is a story far different from the supernatural tales that have long surrounded this region. The development of side-scan sonar technology marked the beginning of a new era in underwater exploration. These systems send sound waves across the ocean floor, creating detailed images of underwater terrain with remarkable clarity. Objects as small as automobiles can be detected and identified from the surface, allowing researchers to map vast areas of seafloor without the expense and risk of deep-sea diving operations. When side-scan sonar was first deployed systematically in the Triangle region, it began to reveal the true extent of human activity in these waters. The ocean floor was littered with the remains of vessels spanning centuries of maritime history, from wooden sailing ships that had succumbed to storms and reefs, to modern steel vessels that had fallen victim to accidents, equipment failures, and human error. Each wreck told a story, and those stories were remarkably consistent with mundane explanations rather than supernatural phenomena. Ships had run aground on coral reefs that were poorly charted or inadequately marked. Vessels had been overwhelmed by sudden storms that struck with little warning. Aircraft had crashed due to mechanical failures, pilot error, or navigation mistakes. In case after case, the evidence pointed to ordinary causes rather than mysterious forces. The discovery of the SS Hewitt, a cargo vessel that disappeared in 1921, illustrates how technology has solved mysteries that once seemed inexplicable. For decades, the ship's disappearance was cited as evidence of the triangle's supernatural nature. The vessel had simply vanished without a trace, leaving no distress signal or debris field to mark its passing. When sonar surveys finally located the wreck in 1987, investigators found that the ship had broken apart in heavy seas, its cargo of steel rails shifting in the storm and causing the vessel to lose stability and sink rapidly. The case of the MV Joyita, which disappeared in 1955 while traveling between American Samoa and the Cook Islands, demonstrates how partial information can create lasting mysteries. The vessel was found 5 weeks after its disappearance, partially submerged and abandoned, with no sign of its passengers and crew. For years, the fate of the 39 people aboard remained a mystery that fueled speculation about triangle-related phenomena. Modern analysis of the wreck, aided by advanced underwater photography and forensic techniques, revealed a more prosaic explanation. The ship had suffered structural damage that caused progressive flooding. The vessel's design, with inadequate watertight compartments, meant that once flooding began, it could not be stopped. The passengers and crew had likely abandoned ship in life rafts, but rough seas and navigation errors had prevented them from reaching safety. Radio equipment damaged by flooding had prevented them from sending effective distress signals. The development of remotely operated vehicles, or ROVs, has provided unprecedented access to deep water wrecks that were previously beyond human reach. These robotic explorers, connected to surface vessels by fiber optic cables, can descend to depths of several miles and operate in conditions that would be instantly fatal to human divers. Equipped with high-definition cameras, manipulator arms, and specialized sensors, ROVs can examine wrecks in minute detail and recover artifacts that provide crucial clues about what happened in the final moments before disaster struck. ROV investigations of triangle wrecks have consistently revealed evidence of conventional causes rather than supernatural phenomena. Metal fatigue, corrosion, and design flaws have been found in vessels once thought to have vanished mysteriously. Fire damage, collision scars, and storm-related structural failures tell stories of human struggle against natural forces rather than encounters with unknown powers. The advent of autonomous underwater vehicles, or AUVs, has further revolutionized underwater exploration. These untethered robots can operate independently for days or weeks, following pre-programmed routes and collecting data across vast areas of ocean floor. Unlike ROVs, which are limited by the length of their connecting cables, AUVs can range freely across the deep ocean, mapping previously unexplored regions and discovering wrecks that have remained hidden for decades or centuries. AUV surveys in the Triangle have revealed an underwater landscape far more complex than previously imagined. Ancient coral reefs, now buried under sediment, create hazards for navigation that early charts could not have anticipated. Underwater canyons and steep escarpments pose challenges for vessels that venture too close to the edge of the continental shelf. Sand waves and shifting sediments constantly reshape the seafloor, creating new hazards and concealing old ones. The precision of modern bathymetric mapping has revealed just how dangerous these waters can be for navigation. Underwater peaks rise suddenly from the depths, coming within feet of the surface before dropping away into abyssal depths. These seamounts, often unmarked on older charts, pose a serious threat to deep draft vessels and have been responsible for numerous groundings and sinkings over the years. Multi-beam sonar systems, which can map entire swaths of ocean floor simultaneously, have revolutionized our understanding of underwater topography. These systems bounce multiple sound beams off the seafloor, creating three-dimensional images of underwater terrain with unprecedented detail and accuracy. Features that were invisible to earlier mapping technologies are now clearly revealed, showing the true complexity of the underwater landscape. The integration of satellite technology with underwater exploration has created new possibilities for wreck discovery and investigation. Synthetic aperture radar satellites can detect surface disturbances caused by underwater wrecks, while satellite-based navigation systems allow precise positioning of search areas. Communication satellites enable real-time transmission of data from deep-sea operations, allowing shore-based experts to participate in underwater investigations as they unfold. Advanced materials science has enabled the construction of vehicles and instruments capable of withstanding the extreme conditions of the deep ocean. Pressure-resistant housings protect sensitive electronics from the crushing weight of water miles deep, while corrosion-resistant alloys ensure that equipment can operate reliably in the harsh chemical environment of seawater. Fiber optic cables provide high-bandwidth communication links that can transmit high-definition video and large volumes of data from the depths to the surface. The development of underwater archaeology as a scientific discipline has brought new rigor to the investigation of shipwrecks. Archaeological techniques adapted for underwater use allow researchers to document wreck sites systematically, preserving information about construction techniques, cargo, and crew possessions that provide insights into maritime history and the circumstances of loss. Computer modeling and simulation have become powerful tools for understanding how ships behave in extreme conditions. Finite element analysis can predict how vessels will respond to various stresses and loads, helping investigators understand how and why particular ships failed. Wave dynamics models can recreate the sea conditions present during historical storms, providing context for understanding how vessels might have been overwhelmed by natural forces. The creation of comprehensive databases of wreck locations and characteristics has enabled researchers to identify patterns in marine casualties that were not apparent when individual incidents were considered in isolation. These databases reveal that the Triangle's accident rate is consistent with other heavily traveled maritime regions, and that the types of accidents that occur follow predictable patterns based on vessel type, weather conditions, and navigation challenges. Modern search and rescue technology has dramatically improved the chances of survival for mariners and aviators in distress. Emergency position indicating radio beacons automatically transmit distress signals when activated by immersion in water or severe impact. Satellite-based search and rescue systems can locate these beacons and dispatch rescue forces with unprecedented speed and accuracy. The Coast Guard's adoption of advanced aircraft and vessels has expanded their search and rescue capabilities far beyond what was possible during the era when many of the Triangle's mysterious disappearances occurred. Helicopters equipped with sophisticated sensors can search vast areas of ocean and operate in weather conditions that would have grounded earlier aircraft. Fast patrol boats and cutters can reach distress locations quickly and operate effectively in rough seas. Electronic chart systems have largely eliminated the navigation errors that contributed to many historical maritime accidents. These systems continuously update vessel positions using GPS and other navigation aids, providing real-time warnings about hazards, shallow water, and restricted areas. Automatic identification systems allow vessels to track each other's movements, reducing the risk of collision in congested waterways. Weather routing services use sophisticated atmospheric and oceanographic models to plan routes that avoid dangerous conditions. Commercial vessels can now receive updated weather information throughout their voyages, allowing them to alter course to avoid storms or other hazardous conditions. This capability has significantly reduced the number of vessels lost to weather-related causes. The implementation of global maritime distress and safety systems has created multiple layers of communication and emergency response capability. Vessels are required to carry various types of emergency communication equipment, ensuring that distress signals can be transmitted even if primary communication systems fail. Satellite communication systems provide global coverage, eliminating the communication dead zones that existed in earlier eras. Despite these technological advances, the ocean remains a challenging and potentially dangerous environment. Modern technology has not eliminated all risks, but it has dramatically reduced them and provided much better understanding of what happens when things go wrong. The mysteries that once surrounded many Triangle disappearances have been solved not through supernatural explanations, but through the patient application of scientific method and technological capability. The transformation of underwater exploration from a dangerous and limited endeavor to a sophisticated scientific discipline represents one of the great achievements of modern technology. The ocean depths that once seemed as remote and inaccessible as the surface of Mars are now regularly visited by robotic explorers that can work for months without human intervention. The seafloor that was once terra incognita is being mapped with the same precision as the surface of the Earth. As we continue to develop new technologies for ocean exploration, the remaining mysteries of the Triangle are likely to yield to scientific investigation. Advanced sensors may detect phenomena that current instruments cannot measure. Improved underwater vehicles may reach areas that are currently inaccessible. Artificial intelligence and machine learning may identify patterns in data that human researchers have overlooked. The story of modern shipwreck investigation in the Triangle is ultimately a story of human ingenuity triumphing over natural obstacles. Through persistence, innovation, and the careful application of scientific principles, we have begun to understand what really lies beneath these mysterious waters. The ocean keeps its secrets grudgingly, but technology is proving to be a key that can unlock even the deepest mysteries. In the quiet moments before dawn, when the ocean stretches endlessly in every direction and the horizon blurs into uncertainty, the human mind becomes both navigator and passenger on a journey through waters that exist as much in consciousness as in reality. Here, in the vast expanse of the Bermuda Triangle, we encounter not just the physical challenges of wind and wave, but the deeper mysteries of human perception, memory, and the stories we tell ourselves about the world around us. The psychology of those who venture into these waters reveals patterns that are far more consistent and predictable than any supernatural phenomena. Fear, fatigue, disorientation, and the simple but profound tendency of the human mind to seek patterns and meaning in random events have shaped the Triangle's reputation as much as any actual incidents that may have occurred within its boundaries. When we examine the documented cases of disappearances and strange encounters in the Triangle, we find again and again the fingerprints of human psychology at work. Stress and fatigue can transform ordinary events into extraordinary experiences. The isolation and sensory deprivation of long ocean voyages can create altered states of consciousness that affect perception and memory. The knowledge of the Triangle's reputation can prime witnesses to interpret normal phenomena as supernatural, creating a feedback loop that reinforces the very myths it seeks to explain. Consider the psychological state of a pilot flying alone over the vast emptiness of the Atlantic Ocean. Hours pass with nothing but water visible in every direction, the monotonous sound of engines creating a hypnotic rhythm that can affect consciousness and attention. The brain, deprived of the normal variety of sensory input it expects, may begin to create its own stimulation, generating visual and auditory hallucinations that seem completely real to the observer. This phenomenon, known as sensory deprivation, has been extensively studied in laboratory settings and is well understood by psychologists and neurologists. Subjects placed in environments with minimal sensory input regularly report seeing lights, hearing sounds, and experiencing sensations that have no external source. For a pilot already aware of the Triangle's mysterious reputation, such experiences may easily be interpreted as encounters with supernatural forces rather than recognized as normal responses to an abnormal environment. The effects of hypoxia or oxygen deprivation add another layer of complexity to psychological experiences in aviation. As aircraft climb to higher altitudes, the reduced oxygen availability can affect brain function in subtle but significant ways. Early symptoms include euphoria, overconfidence, and impaired judgment, effects that may not be immediately recognized by the person experiencing them. More severe hypoxia can cause hallucinations, memory loss, and profound disorientation. A pilot experiencing mild hypoxia might make navigation errors that seem inexplicable to ground observers. They might report seeing things that are not there or fail to see things that are clearly present. Their radio communications might become confused or contradictory. To outside observers, such behavior might seem mysterious or supernatural, but to medical professionals, it represents a well-understood physiological response to oxygen deprivation. The phenomenon of confirmation bias plays a crucial role in how Triangle stories develop and spread. This cognitive bias leads people to selectively notice, remember, and interpret information in ways that confirm their existing beliefs or expectations. A pilot who believes in the Triangle's supernatural properties may notice and remember unusual events while flying through the area, while dismissing or forgetting similar events that occur elsewhere as unremarkable. This selective attention and memory can transform a collection of ordinary experiences into what seems like a pattern of supernatural encounters. The pilot may genuinely believe they have experienced something extraordinary, and their sincere conviction can be compelling to others who hear their story. Over time, small details may be embellished or forgotten, and the story may evolve to become more dramatic and mysterious than the original experience warranted. The power of suggestion influences how people interpret their experiences in the Triangle. Maritime and aviation professionals who are familiar with the region's reputation may approach their journeys with heightened alertness for unusual phenomena. This state of hypervigilance can lead them to notice and attach significance to events that they might otherwise ignore or dismiss as routine equipment behavior or normal environmental conditions. Social and cultural factors also shape how triangle experiences are interpreted and reported. During periods when UFO sightings and paranormal phenomena capture public attention, triangle stories tend to emphasize extraterrestrial or supernatural elements. When public interest shifts to other topics, the same types of experiences may be interpreted differently or may receive less attention altogether. The media's role in shaping triangle stories cannot be underestimated. Dramatic accounts sell newspapers and attract television viewers, creating economic incentives for sensationalizing ordinary events. Reporters may emphasize mysterious aspects of stories while downplaying mundane explanations. Over time, this selective reporting can create a distorted picture of what actually happens in the triangle, making normal maritime and aviation activity seem far more dangerous and mysterious than it actually is. The psychology of memory adds another layer of complexity to triangle stories. Human memory is not like a video recording that faithfully preserves events as they occurred. Instead, it is a reconstructive process that can be influenced by subsequent experiences, expectations, and information. Each time a memory is recalled, it may be slightly altered, and over time, these changes can accumulate to create memories of events that differ significantly from what actually happened. A mariner who experiences equipment problems while sailing through the triangle may initially attribute them to normal mechanical issues. However, if they later learn about the triangle's reputation and hear stories of supernatural phenomena, their memory of the event may gradually change. Details that originally seemed insignificant may become more prominent, while aspects that suggested mundane explanations may fade. Eventually, they may genuinely remember experiencing something that seemed supernatural, even though their original interpretation was quite different. The phenomenon of false memory syndrome demonstrates how powerfully the mind can create vivid recollections of events that never occurred. Under certain conditions, people can develop detailed memories of experiences that seem completely real to them, but that can be shown to have no basis in actual events. While false memories typically develop in therapeutic or investigative settings where suggestive questioning techniques are used, they can also occur spontaneously when people are exposed to compelling stories or suggestions about what they might have experienced. Group psychology and social influence can amplify individual psychological effects. When multiple people share an experience, they may influence each other's interpretation and memory of events through discussion and shared expectations. A crew member who initially noticed nothing unusual may begin to remember strange phenomena after hearing other crew members describe their own experiences. This process of memory contamination can create apparent corroboration for supernatural events when the reality is that normal psychological processes have created false consensus. The availability heuristic, a cognitive bias that leads people to judge the likelihood of events based on how easily they can recall examples, contributes to the triangle's reputation. Because triangle stories are widely publicized and frequently retold, people may overestimate the frequency of mysterious disappearances in the region. They may also underestimate the frequency of similar events in other parts of the world, simply because those stories receive less media attention and are therefore less memorable. Statistical illiteracy compounds these psychological biases. Most people have difficulty understanding probability and statistical significance, making them prone to seeing meaningful patterns in random data. The triangle sees heavy traffic from ships and aircraft, making it statistically inevitable that some percentage of vessels will experience problems or accidents. However, people may interpret this normal accident rate as evidence of supernatural intervention, especially if they are not aware of the baseline rates of maritime and aviation accidents in other busy regions. The psychological concept of attribution error helps explain why triangle stories persist despite logical explanations. When good things happen, people tend to attribute them to their own skill and effort. When bad things happen, they may attribute them to external forces beyond their control. For mariners and aviators, attributing accidents and near misses to supernatural forces in the triangle may be psychologically easier than accepting that they made errors or that random chance played a role in their misfortune. The appeal of mystery and the extraordinary also plays a role in how triangle stories develop and spread. Most people find stories of supernatural phenomena more interesting and emotionally engaging than accounts of equipment failures or navigation errors. This preference for the extraordinary can lead storytellers to emphasize mysterious aspects of their experiences while downplaying mundane explanations, even when those explanations are more accurate and complete. Professional pride and reputation concerns can influence how maritime and aviation professionals report and interpret their experiences. A pilot who becomes lost due to navigation errors might be reluctant to admit their mistakes, especially if their professional reputation depends on their image as a skilled navigator. Attributing the problem to mysterious forces or equipment malfunctions caused by supernatural interference might seem preferable to acknowledging human error. The role of stress and emergency situations in affecting perception and memory cannot be overlooked. When people face life-threatening situations, their stress response can significantly alter their cognitive functioning. Tunnel vision, time distortion, and memory gaps are common responses to extreme stress. People in emergency situations may focus so intently on immediate survival needs that they fail to notice or remember important details about what caused their predicament. After the emergency has passed, the stress of the experience may make it difficult to recall events accurately. The mind may fill in gaps in memory with plausible details that seem consistent with the person's understanding of what happened, even if those details are not based on actual observations. These reconstructed memories may seem vivid and convincing but may not accurately reflect the original events. The psychological phenomenon of dissociation can also affect how people experience and remember triangle encounters. Under extreme stress or in situations of sensory deprivation, some people may experience a sense of detachment from their immediate surroundings or from their own thoughts and feelings. This dissociative state can create experiences that feel surreal or otherworldly, contributing to reports of supernatural encounters. Training and experience play crucial roles in how people interpret and respond to unusual situations. Professional mariners and aviators who have extensive experience with equipment malfunctions, weather phenomena, and navigation challenges are generally better able to recognize and correctly interpret unusual events. However, even experienced professionals can be susceptible to psychological biases and perceptual errors, especially in high-stress situations or when operating in unfamiliar conditions. The power of expectation in shaping experience is particularly relevant to triangle encounters. People who expect to experience supernatural phenomena may be more likely to interpret ambiguous situations in ways that confirm their expectations. This expectancy effect can be so powerful that it can actually influence physiology, causing measurable changes in heart rate, blood pressure, and other biological markers that seem to validate the person's interpretation of their experience. Cultural and generational differences in how people interpret and report unusual experiences also contribute to the triangle's evolving reputation. Older generations who grew up during the height of UFO and paranormal interest in the 1960s and 70s may be more likely to interpret unusual events in supernatural terms. Younger generations raised with greater scientific literacy and skepticism about paranormal phenomena may be more likely to seek conventional explanations. The psychological concept of cognitive dissonance helps explain why triangle beliefs persist even in the face of contradictory evidence. When people have invested time, effort, or emotional energy in believing something, they may experience psychological discomfort when confronted with evidence that challenges their beliefs. To reduce this discomfort, they may dismiss contradictory evidence, reinterpret it to fit their existing beliefs, or seek out confirming evidence while avoiding disconfirming information. Professional debunkers and skeptics sometimes underestimate the psychological power of personal experience in shaping beliefs about the triangle. For someone who has personally experienced what they interpret as a supernatural encounter, no amount of statistical analysis or scientific explanation may be sufficient to change their belief. The vividness and emotional impact of personal experience often outweighs abstract reasoning in determining what people believe to be true. Understanding the psychological dimensions of triangle stories does not necessarily invalidate the experiences of those who report unusual phenomena. The human mind is a complex system that can produce experiences that are subjectively real and meaningful, even if they do not correspond to external physical events. Recognizing the role of psychology in triangle encounters can help us better understand both the limitations of human perception and the remarkable capacity of consciousness to create meaning and narrative from the raw material of sensory experience. The triangle's reputation ultimately rests not on any objective supernatural properties of the region, but on the very human tendency to create stories that give meaning to uncertainty and mystery. In our desire to understand and explain the unknown, we reveal fundamental aspects of human nature that are far more fascinating than any paranormal phenomenon could ever be. In the quiet halls of oceanographic institutions and meteorological centers around the world, a remarkable transformation has taken place over the past several decades. Scientists armed with sophisticated instruments, vast databases, and powerful analytical tools have turned their attention to the waters of the Bermuda Triangle, not to validate supernatural theories or debunk cherished myths, but to understand what actually happens in this corner of the Atlantic Ocean. Their findings paint a picture that is both more mundane and more fascinating than the legends that have grown around this region. The scientific consensus regarding the Bermuda Triangle has emerged gradually, built upon thousands of hours of research, countless measurements, and the patient accumulation of data from multiple disciplines. Oceanographers have mapped the seafloor in unprecedented detail. Meteorologists have analyzed decades of weather patterns. Maritime historians have examined shipping records stretching back centuries. Aviation experts have investigated aircraft accidents with forensic precision. Together, they have constructed a comprehensive understanding of what makes this region unique and what does not. The foundation of scientific analysis rests upon statistical comparison. When researchers examine the rate of ship and aircraft losses in the triangle, they compare these numbers not to an idealized world where no accidents occur, but to similar regions elsewhere in the world's oceans. This comparative approach reveals a crucial truth. The triangle's accident rate is entirely consistent with what would be expected for any heavily traveled maritime and aviation corridor. The National Transportation Safety Board, the agency responsible for investigating aviation accidents in the United States, maintains comprehensive records of aircraft incidents and accidents. These records show no statistically significant increase in accident rates for flights passing through the Triangle region compared to other busy aviation corridors. When accidents do occur, investigation reveals the same causes that are found everywhere else: mechanical failure, pilot error, weather-related incidents, and fuel exhaustion. Similarly, maritime authorities such as Lloyd's of London, which insures a significant portion of the world's commercial shipping, find no evidence that vessels are more likely to be lost in the Triangle than in comparable regions. The company's actuaries, whose job it is to assess risk with mathematical precision, calculate insurance premiums based on actual loss statistics rather than sensational media reports. Their rates for Triangle voyages reflect no supernatural premium. The United States Coast Guard, which has responsibility for search and rescue operations in much of the Triangle region, has perhaps the most direct experience with maritime incidents in these waters. Coast Guard officials consistently report that the types of emergencies they encounter in the Triangle are identical to those found elsewhere: engine failures, navigation errors, medical emergencies, fire, collision, and weather-related distress. Their response procedures and success rates in the Triangle match those for other regions of similar size and traffic density. Oceanographic research has revealed the Triangle to be a region of extraordinary natural complexity, but this complexity operates within well-understood physical principles. The meeting of different water masses creates temperature and salinity gradients that affect everything from marine life distribution to acoustic propagation. The interaction between the Gulf Stream and surrounding waters generates turbulence and eddy formations that can affect navigation and search operations, but these phenomena are thoroughly documented and predictable. The geological structure beneath the Triangle has been mapped with seismic surveys that reveal a seafloor shaped by millions of years of sediment deposition, volcanic activity, and tectonic movement. While this underwater landscape contains dramatic features such as deep trenches, underwater mountains, and steep escarpments, Similar formations exist throughout the world's oceans. The triangle's geology is remarkable for its complexity and beauty, but not for any properties that would affect surface vessels or aircraft in supernatural ways. Atmospheric scientists have conducted extensive studies of weather patterns in the Triangle region, using both historical data and real-time monitoring systems. Their research confirms that the Triangle experiences some of the most dynamic and rapidly changing weather patterns found anywhere on Earth, but these patterns result from well-understood meteorological processes. The interaction between tropical and temperate air masses, the influence of the Gulf Stream on local atmospheric conditions, and the region's position in hurricane-prone waters all contribute to a challenging but entirely natural weather environment. Modern satellite monitoring has revolutionized our ability to observe and understand triangle weather systems. High-resolution imagery can track the development of individual thunderstorms from their earliest formation through their eventual dissipation. Doppler radar systems can peer inside storm systems to reveal the internal structure of dangerous weather phenomena such as microbursts and wind shear. These observations consistently show that triangle weather, while sometimes severe and rapidly changing, operates according to the same physical principles that govern atmospheric behavior everywhere else. The application of chaos theory and complex systems analysis to triangle phenomena has provided new insights into why this region can seem so unpredictable. Chaos theory demonstrates that complex systems can exhibit behavior that appears random even when governed by deterministic physical laws. Small changes in initial conditions can lead to dramatically different outcomes, a phenomenon known as sensitive dependence on initial conditions or the butterfly effect. In the context of the triangle, this means that slight variations in ocean temperature, atmospheric pressure, or wind patterns can trigger the development of severe weather systems that might not occur under slightly different conditions. This natural unpredictability can make the region seem mysterious to those unfamiliar with complex systems behavior, but it does not require supernatural explanations. Computer modeling has become an increasingly powerful tool for understanding triangle phenomena. Sophisticated models can simulate the interaction between ocean currents and atmospheric systems, predicting how small changes in environmental conditions might affect navigation and safety. These models have been validated against historical data and have successfully predicted the behavior of weather systems and ocean currents in the region. The development of comprehensive databases containing centuries of shipping and aviation records has enabled researchers to identify long-term trends and patterns in triangle incidents. These databases reveal that reported disappearances and mysterious events cluster around periods of intense media attention to the triangle, suggesting that publicity rather than actual incident rates drives the perception of increased supernatural activity. Forensic analysis of triangle incidents has benefited from advances in materials science, metallurgy, and accident investigation techniques. When wreckage is recovered from triangle incidents, examination typically reveals evidence of conventional failure modes, metal fatigue, corrosion, impact damage, or fire. In cases where wreckage cannot be recovered, investigators can often reconstruct the probable sequence of events using meteorological data, radar tracks, and radio communications. The statistical analysis of triangle disappearances reveals patterns that are consistent with random distribution rather than supernatural intervention. Incidents occur during all months of the year, all times of day, and under varying weather conditions. There is no correlation between disappearances and lunar phases, solar activity, or other astronomical phenomena that might be expected if supernatural forces were at work. Psychological research has contributed to scientific understanding of the triangle by explaining how normal cognitive biases and perceptual limitations can create the impression of supernatural phenomena. Studies of eyewitness reliability, memory formation, and the influence of expectation on perception provide natural explanations for many reported triangle encounters that might otherwise seem mysterious. The scientific method requires that theories be testable and falsifiable, criteria that supernatural explanations for triangle phenomena generally fail to meet. Alien abduction theories cannot be tested because they invoke technology and capabilities beyond current human understanding. Theories involving parallel dimensions or time portals cannot be falsified because they propose phenomena that leave no measurable traces. In contrast, natural explanations for triangle incidents can be tested against physical evidence and either confirmed or refuted based on empirical data. International cooperation among scientific institutions has enhanced research into triangle phenomena. Data-sharing agreements allow researchers to access meteorological and oceanographic information from multiple countries, creating a more complete picture of regional conditions. Joint research expeditions bring together expertise from different disciplines and nations, fostering collaborative approaches to understanding complex regional phenomena. The application of artificial intelligence and machine learning to triangle research has opened new avenues for pattern recognition and data analysis. AI systems can process vast amounts of historical data to identify subtle correlations that might escape human notice. Machine learning algorithms can be trained to recognize signatures of different types of accidents or weather phenomena, helping researchers classify and understand incidents more effectively. Modern communication and navigation technology has largely eliminated the types of problems that contributed to many historical triangle incidents. GPS navigation provides position accuracy that was unimaginable just a few decades ago. Satellite communication systems enable vessels and aircraft to maintain contact with rescue authorities throughout their journeys. Emergency beacon technology automatically transmits distress signals when accidents occur, dramatically improving rescue response times and success rates. The scientific community's approach to triangle research exemplifies the broader principles of evidence-based inquiry. Researchers begin with observations and data rather than preconceived theories. They seek natural explanations before invoking supernatural ones. They subject their hypotheses to rigorous testing and peer review. They remain open to new evidence while maintaining healthy skepticism about extraordinary claims. This scientific approach has not diminished the triangle's fascination, but has instead revealed it to be a region of remarkable natural complexity and beauty. The interaction of ocean currents and atmospheric systems creates phenomena that are every bit as awe-inspiring as any supernatural explanation could be. The geological history written in the seafloor tells stories of planetary evolution spanning millions of years. The marine ecosystems that thrive in these waters demonstrate the incredible diversity and adaptability of life on Earth. Science has also revealed the triangle to be an important natural laboratory for studying ocean-atmosphere interactions, marine geology, and tropical meteorology. Research conducted in this region contributes to our understanding of climate change, hurricane formation, and marine ecosystem dynamics. The knowledge gained from triangle research has applications far beyond this specific region, informing our understanding of ocean systems worldwide. The consensus among scientists who have studied the triangle is clear and consistent. This region represents a fascinating example of complex natural systems at work, but it shows no evidence of supernatural phenomena or unusual danger. The triangle's reputation appears to be based on a combination of natural hazards that exist in any heavily traveled maritime region, psychological biases that affect human perception and memory, and media sensationalism that has amplified isolated incidents into a mythology of supernatural danger. This scientific understanding does not require us to abandon our sense of wonder about the triangle. Instead, it invites us to appreciate the real complexity and beauty of natural systems that are far more remarkable than any fictional supernatural force could be. The triangle serves as a reminder that our planet contains wonders that continue to challenge our understanding and inspire our curiosity, wonders that become more rather than less fascinating as we learn to understand them through the lens of scientific inquiry. The triangle's true mystery may be not what supernatural forces operate within its boundaries, but how natural forces of enormous complexity and power create an environment that continues to test human skill and ingenuity. In this perspective, every safe passage through triangle waters represents a triumph of human knowledge over natural challenges, a testament to our species' remarkable ability to understand and work within the constraints imposed by the physical world. Science offers not final answers but better questions, not the end of mystery but the beginning of understanding. In the case of the Bermuda Triangle, scientific inquiry has revealed a region that is simultaneously more predictable and more complex than legend suggests, a place where natural forces operate according to physical laws that we can study, understand, and learn to work with rather than against. As we stand at the threshold of a new era in ocean exploration, the Bermuda Triangle beckons not as a realm of supernatural mystery, but as a frontier for scientific discovery. The same waters that once inspired tales of alien abductions and dimensional portals now serve as a testing ground for technologies that would have seemed like science fiction just decades ago. Artificial intelligence guides autonomous vessels through the depths. Quantum sensors peer into the Earth's magnetic field with unprecedented precision, and robotic archaeologists map the seafloor with the patience and thoroughness that only machines can provide. The future of triangle research lies not in the validation of supernatural theories, but in the continued exploration of natural phenomena that are every bit as remarkable as any fictional mystery. Advanced technologies are revealing secrets hidden beneath the waves for millions of years, while sophisticated analytical tools are helping us understand the complex interactions between ocean, atmosphere, and geology that make this region one of the most dynamic environments on Earth. Artificial intelligence is transforming how researchers analyze the vast amounts of data generated by modern ocean monitoring systems. Machine learning algorithms can process decades of satellite imagery to identify subtle patterns in ocean color, temperature, and surface conditions that might escape human notice. These AI systems can correlate weather patterns with oceanographic data, navigation records with accident reports, and geological features with marine life distributions to create comprehensive models of how the triangle's complex systems interact. Deep learning neural networks, trained on thousands of hours of sonar data, are becoming increasingly sophisticated at identifying and classifying objects on the seafloor. These systems can distinguish between natural geological formations and artificial structures, automatically flagging potential wreck sites for further investigation. As these AI systems become more capable, they may discover wrecks that have remained hidden for centuries, finally solving some of the historical disappearances that contributed to the triangle's mysterious reputation. The development of swarm robotics promises to revolutionize underwater exploration. Instead of deploying single, expensive autonomous vehicles, researchers are beginning to experiment with coordinated fleets of smaller, simpler robots that can work together to map vast areas of ocean floor. These robotic swarms can adapt to changing conditions, share information in real time, and continue operating even if individual units fail, providing a level of redundancy and coverage that was previously impossible. Quantum sensing technology represents one of the most exciting frontiers in triangle research. Quantum magnetometers can detect magnetic field variations with sensitivity that exceeds traditional instruments by orders of magnitude. These devices may be capable of identifying subtle magnetic anomalies associated with geological structures, underwater mineral deposits, or even the iron components of shipwrecks buried beneath sediment. As quantum sensors become more portable and practical, they may reveal aspects of the triangle's magnetic environment that have never been detected before. Biotechnology is opening new avenues for understanding the triangle's marine ecosystems. Environmental DNA sampling can identify species present in water samples even when the organisms themselves are not directly observed. This technique is revealing the hidden diversity of marine life in triangle waters and helping researchers understand how oceanographic conditions affect biological communities. Some researchers speculate that unusual marine life distributions might explain historical reports of strange phenomena, as bioluminescent organisms or unusual fish behavior could create optical effects that might be misinterpreted as supernatural. Advanced materials science is enabling the construction of research vessels and instruments that can operate in conditions previously considered too extreme for scientific study. Ultra-deep submersibles built with new composite materials can descend to the deepest parts of the Puerto Rico Trench, while underwater vehicles equipped with advanced life support systems can operate for months without returning to the surface. These capabilities are opening previously inaccessible regions to scientific investigation. Satellite technology continues to evolve in ways that will enhance triangle research. Next-generation Earth observation satellites will provide higher-resolution imagery, more frequent coverage, and new types of sensors capable of detecting phenomena that current satellites cannot observe. Synthetic aperture radar satellites may be able to detect underwater features and currents with greater precision, while hyperspectral imaging systems could identify the chemical composition of surface waters and detect pollution or other environmental changes. Climate change research is becoming an increasingly important aspect of triangle science. As global temperatures rise and ocean circulation patterns shift, the triangle's unique oceanographic and atmospheric conditions may change in ways that affect everything from hurricane formation to marine ecosystem health. Long-term monitoring programs are being established to track these changes and understand their implications for navigation safety, marine life, and coastal communities. The integration of blockchain technology with ocean monitoring systems may revolutionize how research data is collected, verified, and shared. Distributed sensor networks could use blockchain protocols to ensure that environmental data cannot be tampered with or falsified, creating trusted records of oceanographic conditions that could be valuable for both scientific research and legal purposes. This technology could be particularly useful for tracking pollution, documenting climate change impacts, and verifying the circumstances surrounding maritime incidents. Virtual and augmented reality technologies are transforming how researchers visualize and interact with triangle data. Scientists can now explore three-dimensional models of the seafloor, examine shipwrecks in virtual reality, and manipulate complex datasets using gesture-based interfaces. These immersive technologies are not only making research more efficient, but are also enabling new forms of collaboration between researchers at different institutions around the world. Citizen science initiatives are beginning to involve the public in triangle research in unprecedented ways. Smartphone apps can turn ordinary sailors and pilots into data collectors, recording GPS tracks, weather observations, and marine life sightings that contribute to scientific databases. Crowdsourced analysis platforms allow volunteers to help identify features in satellite imagery or classify underwater photographs, effectively multiplying the analytical capacity available to researchers. The development of new underwater communication technologies promises to improve safety and research capabilities in triangle waters. Acoustic networks can enable real-time communication between submerged vehicles and surface vessels, while optical communication systems using laser light can provide high-bandwidth data transmission through seawater. These technologies will allow for more sophisticated coordination of research operations and faster response to emergency situations. Advanced weather prediction models, powered by machine learning and running on supercomputers, are providing increasingly accurate forecasts of triangle weather conditions. These models can predict the formation of microbursts, the development of rogue waves, and the track of tropical cyclones with precision that was unimaginable just a decade ago. As these forecasting capabilities continue to improve, they will significantly enhance safety for vessels and aircraft operating in the region. Space-based research platforms may also contribute to triangle science in unexpected ways. The International Space Station and other orbital laboratories provide unique vantage points for observing Earth's ocean and atmosphere systems. Astronauts can observe and photograph weather phenomena, ocean currents, and other features that are difficult to study from surface-based platforms. As commercial space stations become operational, they may provide additional opportunities for Earth observation research. Genetic sequencing technology is revealing the evolutionary history of marine life in triangle waters, helping scientists understand how species have adapted to the region's unique conditions over millions of years. Some organisms may have evolved specialized capabilities for dealing with rapid environmental changes or extreme conditions, and studying these adaptations could provide insights into the fundamental biology of life in dynamic ocean environments. The application of complexity science and network theory to triangle research is helping scientists understand how seemingly unconnected phenomena may be linked through subtle feedback loops and emergent properties. These approaches may reveal why certain combinations of oceanographic and atmospheric conditions seem to produce disproportionately dramatic effects, helping explain why the triangle region can seem so unpredictable even when individual components are well understood. Nanotechnology applications in ocean research are beginning to emerge with microscopic sensors that can be deployed in large numbers to monitor water chemistry, temperature, and biological activity at unprecedented spatial and temporal resolution. These nanosensors could create detailed maps of how conditions vary throughout triangle waters, potentially revealing small-scale processes that influence larger-scale phenomena. Advanced archaeological techniques adapted for underwater use are revolutionizing the study of shipwrecks and other submerged cultural resources. Photogrammetry can create detailed three-dimensional models of wreck sites, while ground-penetrating radar adapted for underwater use can detect buried artifacts and structural features. DNA analysis can sometimes identify the origins of wooden ships or the species of animals whose bones are found in cargo holds, providing detailed information about historical trade routes and maritime practices. The development of hybrid renewable energy systems specifically designed for ocean research platforms is extending the duration and range of scientific expeditions. Solar panels, wind turbines, and wave energy converters can power research vessels and autonomous platforms for extended periods, reducing the need for fuel resupply and enabling long-term monitoring programs in remote areas of the Triangle. As research capabilities continue to advance, the focus of triangle science is shifting from debunking supernatural theories to understanding and predicting the complex natural systems that operate in this dynamic region. Future researchers will likely concentrate on questions such as how climate change will affect regional weather patterns, how shipping traffic impacts marine ecosystems, and how technological advances can improve safety for those who work and travel in these waters. Educational applications of triangle research are also evolving. Virtual reality systems allow students to explore triangle waters without leaving the classroom, while interactive computer models let them experiment with different scenarios to understand how changes in ocean or atmospheric conditions might affect navigation or marine life. These educational tools are inspiring a new generation of ocean scientists and maritime professionals who will continue the work of understanding and protecting this remarkable region. The international cooperation that has become essential to modern triangle research is likely to expand as countries recognize the value of shared data and coordinated research efforts. Global challenges such as climate change, ocean pollution, and sustainable resource management require collaborative approaches that transcend national boundaries. The Triangle, as a region that affects and is affected by global ocean and atmosphere systems, serves as an ideal laboratory for developing these collaborative research models. Perhaps most importantly, future triangle research will continue to demonstrate the power of scientific inquiry to transform mystery into understanding. Each new discovery, each technological advance, and each insight into natural processes adds to our collective knowledge and helps us better appreciate the remarkable complexity and beauty of our planet's ocean systems. The Triangle of the future will not be a place of supernatural danger, but a showcase for human ingenuity and scientific achievement. It will serve as a reminder that the natural world contains wonders far more remarkable than any fictional mystery, and that understanding these wonders through careful observation and rigorous analysis is one of humanity's greatest accomplishments. As we look toward this future, we can anticipate discoveries that will surprise and delight us, technologies that will seem magical even as they operate according to well-understood scientific principles, and insights that will deepen our appreciation for the intricate systems that govern our planet's behavior. The Triangle's greatest mysteries may not be what supernatural forces operate within its boundaries, but what new understanding of natural processes its continued study will reveal. As our journey through the waters of the Bermuda Triangle draws to a close, we find ourselves not at the end of mystery, but at the beginning of understanding. The ocean that stretches before us in the gathering twilight holds the same secrets it has always held, but we see them now with different eyes. Where once we might have seen supernatural forces at work, we now recognize the intricate dance of natural systems operating according to physical laws that we are only beginning to fully comprehend. The Triangle's reputation was indeed built on mystery, but not the kind of mystery that requires alien intervention or dimensional portals to explain. It was built on the deeper mystery of how our planet's complex systems interact, how seemingly small changes can cascade into dramatic effects, and how the meeting of different air masses and water bodies can create conditions that challenge even our most sophisticated understanding of natural processes. In the gentle lapping of waves against unseen shores, in the whisper of wind across endless water, we hear not the voices of otherworldly beings, but the conversations between ocean and atmosphere that have been going on for billions of years. These conversations speak of forces so vast and interconnected that they dwarf any supernatural explanation humans have ever devised. They tell stories of energy moving through systems on scales of time and space that stretch our imagination far beyond the comfortable boundaries of human experience. The scientists who have dedicated their careers to understanding these waters have not diminished the triangle's wonder by explaining its phenomena. Instead, they have revealed it to be something far more remarkable than any fictional mystery could ever be. They have shown us a region where the fundamental forces that shape our planet are on constant display, where the boundary between solid Earth and liquid ocean becomes a stage for performances of incredible complexity and beauty. What we have discovered in our exploration is that the true magic of the Bermuda Triangle lies not in its ability to defy natural law, but in its perfect embodiment of natural law, in all its intricate glory. The currents that flow through these waters carry with them the thermal energy of tropical seas and the momentum of planetary rotation. The storms that form here draw their power from the vast heat engine of the sun working on the ocean's surface, creating atmospheric disturbances that can span hundreds of miles and affect weather patterns across entire continents. The seafloor beneath these waters tells a story written in stone and sediment that spans millions of years. Each layer of the ocean bottom preserves a chapter in the history of our planet, recording changes in climate, the rise and fall of sea levels, and the slow drift of continents across the face of the Earth. The triangle sits atop this geological library, a repository of information about our planet's past that we are only beginning to learn how to read. The marine life that inhabits these waters has evolved over countless generations to take advantage of the unique conditions created by the meeting of different ocean systems. From microscopic plankton that form the base of elaborate food webs to great whales that traverse ocean basins in their seasonal migrations, the triangle supports ecosystems of remarkable diversity and resilience. These living systems respond to changes in ocean temperature, current patterns, and chemical composition with a sensitivity that often exceeds our most sophisticated instruments. Yet for all our growing understanding of the triangle's natural systems, questions remain that may keep researchers occupied for generations to come. How exactly do the complex feedback loops between ocean and atmosphere operate in this region? What role do subtle variations in underwater topography play in shaping current patterns and weather formation? How will climate change affect the delicate balance of forces that makes this region so dynamic? These are not supernatural mysteries, but scientific puzzles that invite continued investigation and discovery. They represent the kind of challenges that drive human curiosity and inspire the development of new technologies and research methods. In pursuing answers to these questions, we not only deepen our understanding of the triangle, but also advance our knowledge of how ocean systems work throughout our planet. Perhaps the most important lesson of our journey through triangle science is that mystery and understanding are not opposites, but partners in the dance of human knowledge. Each answer we discover leads to new questions. Each explanation reveals new complexities that we had not previously imagined. The triangle teaches us that science does not eliminate wonder, but transforms it, turning vague fears and supernatural speculations into specific questions that can be investigated and understood. The pilots and mariners who venture into triangle waters today carry with them the accumulated wisdom of centuries of human experience in these challenging conditions. They navigate with instruments that can pinpoint their location to within meters, communicate with rescue services via satellites that orbit high above the Earth, and receive weather forecasts that predict conditions hours or days in advance. Yet they also carry with them the knowledge that the ocean remains a powerful and sometimes unpredictable force that demands respect and careful preparation. The stories of mysterious disappearances and supernatural encounters that built the Triangle's reputation may have been based more on perception than reality, but they reflect genuine human experiences of confronting forces larger than themselves. The awe and fear that the open ocean can inspire are real emotions that speak to our recognition of nature's power and our own vulnerability. These feelings do not require supernatural explanations to be meaningful or important. The media sensationalism that amplified isolated incidents into a mythology of supernatural danger served to remind us of the human need for mystery and meaning in an increasingly scientific world. While the specific claims about alien abductions and dimensional portals may have been unfounded, they reflected deeper truths about human nature and our relationship with the unknown. The triangle became a focal point for hopes and fears that had little to do with the actual conditions in these waters, but everything to do with our collective psychology and cultural needs. As technology continues to advance and our understanding of natural systems deepens, the triangle will likely lose much of its supernatural reputation while gaining recognition as one of the most scientifically interesting regions of our planet's oceans. Future researchers will study these waters not to validate paranormal theories, but to understand the complex interactions between geological, oceanographic, atmospheric, and biological systems that make this region unique. The educational value of triangle research extends far beyond the boundaries of this specific region. The lessons learned from studying these dynamic waters apply to ocean systems throughout the world, helping us understand how currents transport heat and nutrients across ocean basins, how storms form and intensify over warm water, and how marine ecosystems respond to environmental changes. The triangle serves as a natural laboratory where principles discovered through careful observation can be tested and refined. In our age of rapid technological change and global environmental challenges, the triangle reminds us of the importance of understanding natural systems that operate on scales much larger than individual human lives. The currents that flow through these waters affect climate patterns across the Atlantic basin. The storms that form here can impact communities thousands of miles away. The marine ecosystems that thrive in these conditions play important roles in global ocean chemistry and carbon cycling. The triangle also serves as a reminder of how human perception and cultural factors can shape our understanding of natural phenomena. The same waters that inspired tales of supernatural danger have also been the scene of countless safe passages and successful rescues. The difference often lies not in the objective conditions, but in how those conditions are interpreted and reported. Understanding these psychological and cultural dimensions of perception is as important as understanding the physical processes that occur in the ocean itself. As we bid farewell to the triangle and return to shore, we carry with us not just knowledge but wisdom. We have learned that the natural world is far more complex and wonderful than any supernatural explanation could capture. We have discovered that mystery does not require the abandonment of reason, but rather its careful application to phenomena that stretch the limits of our current understanding. The waves that wash against distant shores will continue their eternal rhythm long after our names are forgotten. The currents that flow through these waters will carry heat and life across ocean basins for millions of years to come. The storms that form here will continue to demonstrate the awesome power of natural forces operating according to physical laws that we can study but never fully control. In this perspective, the Bermuda Triangle becomes not a place to be feared, but a source of inspiration and wonder. It reminds us that we live on a planet of incredible beauty and complexity, a world where the simple interaction of sun, sea, and atmosphere can create phenomena that challenge our understanding and reward our curiosity. The greatest mystery of the triangle may not be what forces operate within its boundaries, but what new discoveries await those brave enough to continue exploring the endless frontier of scientific knowledge that surrounds us on every side.